Okay, Gabriel's horn is a thing in mathematics which has a kind of paradoxical nature to it. When you've done some C4, you'll have done a lot of the mathematics that we're going to do here today. But I'll quickly talk you through some of the results. So we're going to start off looking at a graph of y equals 1 over x, which looks like this. So y equals 1 over x. So for positive x values, as x gets smaller and smaller, closer to 0, we get a really big y value. So it starts up here, and as x increases, it goes like this. Similarly, if y is a negative number but close to 0, we get the same kind of thing but negative y. So it starts here, it goes like this. Now, one of the things that you'll do quite a lot when you do C4 is deal with volumes of revolution. So if we imagine taking the shape and spinning it around the x-axis to make a 3D shape, what we do, if we just take the positive part of x here, we get a kind of horn shape. So we get something like this. So it'd be wide at one end, and it would get wider and wider, like as you got closer and closer to 0. And then this thing would very quickly come in, something like that, and it will get infinitely close to each other, because it would be like two asymptotes, so doubly, it will get to itself doubly quick because it's asymptoting from both sides. But a natural question is, can we work out the surface area of that shape, and can we work out the volume of that shape? Now, if we let the shape go all the way to 0, then it would become infinitely wide at one end. So a convenient starting point is, if we cut it off at one point, if we cut it off when x equals 1, there, which would be when y equals 1. So what I'm taking is just this part of the shape onwards, because that gives it a nice bound on one end of it. Well, we've got a whole lot of formulas, they're in the formula book, that we can do to work out the volume and the surface area. I'm going to start with the volume, because it's easier. So the standard thing for the volume will be, if we go from x equals 1 to a, and in a minute we'll let a get bigger and bigger, then the volume is going to be pi times the integral of this to this, so 1 to a, which again we can make a bigger in a minute, of y squared. Now y squared in this case is 1 over x, well y is 1 over x, so y squared is 1 over x squared. Dx. Well, we know how to do that integration, it's C2 integration. So we can think of this as x to the minus 2, which gives us pi, if we add 1 to the power, we've got minus 1, divided by the new power, we've got minus 1 over x, 1a. And if we put those things in, if I put in the a into here, I've got minus pi over a, minus pi, which, if we neaten it up, that's pi 1 minus 1 over a. Okay, cool. Well, we can talk about what happens now as a tends to infinity. If a tends to infinity, i.e. we go further and further along, then the volume here, well, 1 over a will tend to 0, so the volume is going to get closer and closer to just being pi. It's very much finite. So even if we go an infinite distance here, we're adding such a small amount as we go along, we still got a finite volume, which is just pi. Cool. Let's do the same thing with the surface area. So we've got a very similar formula for the surface area. Surface area, this time it's 2 pi times the integral from 1 to a again, so same sort of format. Now it becomes a bit trickier, but we're going to have 1 over x times the root of something quite complicated. So we get 1 plus minus 1 over x squared dx. That thing's atrocious. Again, once you've done some C4, you'll see where we get this from, but this is dx dy all squared. Don't worry about it. But we're not going to evaluate this thing properly. We're going to treat it with an inequality here. This thing in here, well, if we square something, it's definitely positive. 1 plus that thing is definitely something a bit bigger than 1. And if we square root it, we've still got something a bit bigger than 1. So this whole thing is slightly greater than 2 pi times the integral from a to 1 of 1 over x dx. Because this thing is just a bit bigger than 1. So it's slightly bigger than this thing if it was just 1. But this thing we can evaluate quite easily. The integral of 1 over x is log x, or log mod x. So this thing here is 2 pi times log x a1. Putting those bits in, we've got 2 pi times log a, and if we put the 1 in, log of 1 is 0, so it just cancels. And so we've got this thing here. And again, we're going to do the same thing now. The argument is we're going to take a and we're going to bring it further and further along to let it tend to infinity. The limit of this, well, log of something getting bigger and bigger, something tending to infinity, is still infinity. It gets there slowly, but it's still going to get to infinity. So this thing is going to get infinitely big, but the actual result is even bigger than that, because we set up our inequality that way. So the surface area of this thing, the actual full length one, is infinite, whereas the volume is finite. Now the paradox here is, we highlighted it in the 17th century, actually by doing a different method rather than calculus to get here, and we got to the same problem. If you imagine taking this horn, turning it up, so we've got the top of it here, and then filling it with paint, well, it's got a finite area, it's got a finite volume. It's going to tend to pi, so we get pi, well, whatever the unit is, volume of paint, and we pour it into our horn. Well, because it gets infinitely thin at the bottom, we're still going to have, it will get full of paint. We won't be able to put an infinite amount in. We'll be able to put in 3 and a bit. But because it's got infinite surface area, that paint which fills it won't be able to colour the whole of the inside. Because that won't require an infinite amount of paint, right? This was the paradox. Cool. I'll leave it there. Gabriel's horn.